So our next presenter is Samuel Maraschin.
Yeah.
That's okay. And will present us a modeling and prototyping of a microfluidic device for DNA amplification. Your presentation will be in English.
Yes. Will
Okay,
be
thanks.
English. Just let me check
Let's
how
start.
I share my presentation over here.
Yes, okay. You got a small screen on the
Okay.
bottom.
Mhm.
So you got 15 minutes, and then we got a small 5 minutes time slot for questions.
Great. So, are you guys seeing my presentation?
Yes,
Okay, great.
let's go.
So I am researching here at Unicinos, which is a university on the southern of Brazil, and I working at IoT chip, and mostly we work with MEMS and microfabrication sensors whatsoever. So my work is titled as modeling and prototyping of a microfluidic device for DNA amplification. So basically, just a background, DNA amplification is very useful tool for molecular biology, and nowadays it's being widely used for COVID testing, and it basically has three basically steps to perform that. The first one is named denaturing, where the strands of DNA are separated, and after that, there is a chemical compound named primers that binds with certain region of the DNA. And the last step is the extension step, where the strands are bind together. Each time the cycle is performed, the DNA content of this on certain sample is double. And by doing that, what we can do is see if there is a certain gene that are on the sample that can be related to certain pathogens, such as the COVID itself. So there, the thermocycling is done by three temperatures, 95, 55, and 72 Celsius degrees. So once this is done several times, let's say it depends on the protocol that's being used, but usually this is done at least 40 times. So it takes a while to do that, and this can be something that delays the diagnostics. So in order to do this faster, I I I thought to prototype a microchip with a microchannel on it to do this quicker and more affordable. So uh, microfluidic devices has been widely used over the times, and it started in early 90s. And the great advantages of those devices are to be able to do a several process on a small footprint chip. So there are several types of microfluidic devices, since pretty cheaper ones such as paper microfluidic devices, and there are another ones more sophisticated, such as this one you guys are seeing on the middle of the screen, and that can have several processes and several inputs. And also, there is a possibility to include some electronics parts on that. to get some, let's say, some signal from the sample, and thus getting some sensing from that. So basically, my work here is only to physically modeling the device to see if I could achieve the temperatures required to the thermal processing. Develop a fabrication process to fabricate these devices, and to finish characterization of the devices as such temperatures and geometries results. So I separate the project as physical modeling that was performed on console and SolidWorks software. And then the fabrication process, I divided into 3 steps. The Microchinus fabrication, the PCB with the heaters, and the final assembly that is basically to put together the microchannels and the PCB. And the last one, the characterization. So here is the design that I made. Basically, it has 3 heaters, and it was done on a PCB with a 5 micrometers copper thickness layer, and the heater distance was varied into 1 to 3 millimeters. The microchannel here you cannot see, but this is a lot of several meandering channels here that are 50 micrometers wide and 30 micrometers height. And to insulate the copper from the sample, I did a thin layer to insulate the copper from the sample to avoid contamination on the sample. So here are a more detailed figure, and as you guys can see, there are 4 connections here to heating control. And here is a zoom on the microchannels on top of the heaters. So basically, I started with physical modeling, where I set up the material selection to be able to simulate the device on the software. I select the physics that I would be using, such as Joule effect and fluidic dynamics. And after that, I couple those physics to be able to see the combination of the both of them working together. And lastly, I generated a mesh where each point of this mesh, it would be calculated a value. For my case, this value was a temperature. So going to the results, the first heater distance that I simulated was 500 micrometers between each heater, and what I could get from that is that the hottest heater would interfere several of the other ones by doing this by this distance, and it was doing to thermal crosstalk between the heaters. So here are the values of currents that I used to heat, and therefore I moved to increase the heater distance. So I did another modeling, doubling the heater distance by 1 millimeter. I even turned off the middle heater over here that was no applied current here. And even though I couldn't get satisfied temperatures here due to crosstalk, so the middle heater should have at least 55 degrees, and it was near 8 degrees. So I increased even more the heater distance to 3 millimeters, and even so, it was not possible to achieve 55 degrees on the middle heater. So, in order to fixing that, I conclude that it was not possible doing that with small distances. So instead of performing a cycling, starting from this zone to after the middle zone and the third zone here, one cycle would be accomplished only by using this top heater as the first zone, the third heater as second zone, and using the middle heater to the last zone to extension. If you guys remember the sequence of the amplification. So what resulting is the length of the amplification increased a little bit more, but even so, we can get by doing that we can get a small heater distance to decrease the ship size. So going to fabrication process, I use a process called soft lithography, and this is a process developed by Whitesides on 2000, and it basically models a mold using thick photoresist, and after the mold is done through conventional lithography process, a polymer is casted onto that mold. In this case, to microfluidic is a very popular material to be used is PDMS, that is polymethylsiloxane. So after the mold is cast on the mold, it is released, and the final results are shown on the right side of the slide here. After the microchannel was ready, I processed the PCB to assemble the heaters, and it was a very conventional process to PCB. I used dry film as photoresist, and then I etched the copper using standard etchants, and the final results are also shown here on the bottom side of the figure. The insulation layer was also used the PGMS. It was spin coated on the PCB. A final layer thickness of 10 microns was achieved, and after the PCB and the microchannel was ready and done, I bind them together using plasma process to do that. So what I did was cleaning on the PCB with PGMS layer on it, and I also cleaned the bottom sample of the microchannels, and then I put them together. And after that, I did even a baking process to strengthen the binding. It was a very it was a very powerful binding mechanisms that occurs here due to covalent bonds that are generated on the interface of these materials. So here are some results of characterization. Here is the measuring of the height of the mold to do these microchannels. It got around 25 micrometers height, and by length we got a distance of 7.1 micrometers. Here as the final considerations, as I mentioned earlier on the presentation, it was not possible to achieve this conventional process here, 95, 55 to 72 degrees, due to crosstalk between the thermal crosstalk between the heaters, and therefore we propose an increase on the distance of the cycle procedure to be able to accomplish the temperatures required to DNA amplification. Here are some final simulation results with a 3 millimeters distance between the heaters, and using those currents mentioned here, you can realize that the middle heater require a really small current to reach the temperatures. And here are some final pictures on the assembly. I just put some random fluids just to see if there was some kind of leaking on the device, or if the microchannel was properly in place. So the alignment was good. There was no leakage observed, but unfortunately, due to ethical process that is currently being done, we were not able to do testing with biological samples, so we could not get results with proper DNA amplification. And final remarks are it was possible to prototype a device to DNA amplification. Adjustments on physical model were required, and future works include to, as I told you, do this biological testing, and also put some electronics on the top of the ship here to do this just on only one, to put all together on device. And that's all. Thank you, guys. Okay.
Sorry. Thank you very much, Samuel. With me. So, question for Samuel? Any question, please make in the question and answer section of the chat. Samuel, I got one question. You have you tested yet even you have not biological test? Have you tested because you fabricated the prototype?
Mm-hmm.
but the results you show are simulated ones. So have you tested? You mentioned that there were simulated ones. Have you tested to compare simulations, or still you still have to done this the characterization of the?
Mm-hmm. Yeah, actually, I did some temperature measurements on the heater itself, but without any sampling on that. I just once I put the insulation layer on top of the
Okay.
PCB, I measured the temperatures to see if those current values was enough to reach the temperatures. But I am moving on the process to get ethical acceptance to be able to move for the testing.
Okay. And a final question: when you in the last slide mentioned that the sea work to do in the control system control electronics, you mean
Yeah.
any kind of closed feedback loop, or?
Yeah, actually, as I just did a simple test to see if the currents, I use a proper lab source to input the current over there. But once the once the once the sample is on the channels, I think it will be necessary a closed loop feedback to keep this temperature stable during the thermal cycling. Yes.
Well, okay. Any other question? Okay, thank you very much, Samuel.